Welcome everybody to our fourth lecture on the Coming Up to Speed summer course. Before we start, an announcement. I promised that I was going to take you all for ice cream today. The daily store is closed on Mondays, so we cannot go for ice cream. And I realized that 10 minutes ago, had I realized it before, I would have bought ice cream on Sunday and just bring the ice cream to you. But we're going to try to do this on Wednesday. On Wednesday, they might be closed because it's a federal holiday that I think MSU is not on the official calendar for holidays for MSU. So we'll see if it's open or not. I'm fully planning. Go ahead.
Do we not have class on
So
Wednesday?
that's my next announcement. Because of the tight schedule we have, I am planning on having the class as normal. I checked with the lab and MSU and they have normal activities. But the reason why I feel confident on doing this is because the classes are recorded. So if you are planning on taking that holiday and celebrating all that it means, please go for it and you can see the lecture that we will have afterwards in the video. So don't feel bad at all. It will be me and Josh if nobody else comes, or me alone if Josh also takes that holiday. And I have absolutely no problem with talking to the audience that will see us through generations to come in the YouTube channel. That is the sequence of events. Most likely then, actually now that I'm thinking about it, let's do the ice cream next month on Monday. That way we can celebrate that, no? The next Monday, okay, next Wednesday. Thank you, Andrew. Next Monday is also Monday and the daily store is also closed. Let's do it next Wednesday and that way everybody can come. So that is the sequence of events. And next Monday, I fully expect that we're going to be starting already classical mechanics. This Wednesday, sorry, we are going to close with whatever else leftovers from linear algebra. And we're going to start the miscellaneous topics for math. I plan to talk about Fourier transforms, special functions like Dirac delta functions and Heaviside functions. There was something else in my list. I don't remember. Maybe we'll talk about variational calculus, but actually that is something, okay, I want to put that in the to-do list. Josh, help me not forget, or if you have access to the editing, add as part of that homework to suggest topics for Wednesday. I can literally improvise and start talking about topics that you put in there Wednesday morning. But if you put them between today and tomorrow of extra things that you would like me to at least address from the math point of view, I will be more than happy to touch on those on Wednesday. Sounds good? No, just put it in the playground 4. And yeah, maybe we put maybe we need a Google form. Make a Google form, put it in the link in the thing, and thank you. Okay, so for today, as usual, I'm going to make a summary of a couple of things. As we usually start, be nice to each other, please, and follow the code of conduct. I'm very happy to announce that I haven't had a single issue with any of you. I didn't expect to, but good job for behaving well. This is a list of the resources. Now I have a beautiful picture of me holding an arrow from the channel. I am not going to highlight anything from the GitHub today. That will be part of your homework later. But this is a summary of what we discussed last time. And you can see I had discussed with ChatGPT to transform this screenshot into a raccoonish version of myself. And I think it did a very good job, including the glasses. So I'm happy with it. Okay, so last class, what we discussed mainly was differential equations and vectors and projections. For differential equations, the things that I would like for you to remember or to have as connection thoughts is that differential equations are the rules of a game that we're playing with functions. You define the rules, that is how the differential equation looks like, and then you play the game, evolve the function either in time or in space or in whatever is your variable that you're playing with, and you see how things evolve, and that is your game. Congratulations, you're playing that specific game. The ways of solving differential equations, in my mind at least, you have 3 options, either by memory. You have seen this differential equation already so many times. That is your friend. You already know by memory what should be the solution. My opinion is that you should at least know 2 solutions by memory because they appear over and over and over in many physics applications. The first one is f prime is equal to a number times f, or an operator times f, or a palm tree times f. Anybody can tell me what is the solution to that differential equation?
An exponential.
An exponential, fantastic. E to the lambda x times a constant. So very good, thank you. What about the second equation? F double prime is equal to minus a number times f. Who's the solution for that?
A sinusoid.
Sinusoid, sine, sine, cosines. So that's the two things that you should try to commit to memory and be able to fire them as solutions as soon as somebody asks you what is the function that satisfies this equation. The other two ways of solving differential equations is what I will call math gymnastics. We will see that whenever we're trying to solve the quantum harmonic oscillator, you start playing a bunch of tricks until eventually the differential equation is actually solvable by the means that you know. But that works only on a few cases. That's why most of the solutions that I expect all of you to have in your life whenever you solve differential equations is through computers. So you need to learn a few ways to solving differential equations through the computer. One of the ways that we discussed last class was Euler's method, or the shooting method. And eventually we're going to discuss finite differences. Probably when we're dealing with quantum mechanics, I will show you how to play with them. We also play with two actual mechanical systems, or two games that I like to call them. The one is the oscillatory pendulum, in where this is the differential equation that you have, and you were challenged to try to solve this numerically and see if your solution agrees more or less with what we were looking at. And the other one was a spring that was oscillating up and down. This is the differential equation that it solves. Or at least this is the model that we're using as a differential equation for this system. If you make, in the first case, the small angle approximation, meaning that you say sine of theta, that is just theta, because, you know, small angles, sines, Taylor series, we're all experts. According to Anand, sine of something just looks like something. If you're very close to that something being zero, you get two differential equations that are basically the same differential equation. And what is the solution to these differential equations? I'm realizing that I have a minus sign. This is wrong. This should be a plus. Okay, I will fix that plus later, because it should be 2 derivative on the function is equal to minus a number times the function, not plus. So I screwed up. But without the screw up, what is the solution to those differential equations?
A sinusoid.
Sinusoid. Thank you so much, because it's f prime prime is equal to minus number times f. Everybody's seeing that, or I have somebody that is lost on that thing? Yes? And you know it by heart. Whenever you see a pendulum, what is a pendulum going to do? It's going to oscillate, sines and cosines. What is going to do the spring oscillating with the mass? It's going to oscillate. Okay. We also talk about vectors and projections. We're going to talk more about vectors today. But what things that we discuss is that vectors, you can imagine them as arrows, but they can mean many different things. They can represent little arrows. They can represent coordinates in space. They can represent coordinates in things that are not space. They can also represent functions. Heck, you can represent almost anything with a vector, which is just a list of numbers. I can grab pictures. If I were to take pictures of your faces, and I'm trying to do a machine learning classification algorithm to be able to predict the face of which person I'm looking at, one of the ways is to grab the face and make a long list with zeros and ones if you are converting the picture to black and white. And then that is a vector, which is a very abstract arrow in a very high dimensional space that represents your face. We talk about projections, and projections in terms of vectors are characterized by the dot product. Whenever you're talking about normal vectors in Rn, or R2, R3, 3D, 2D, etc. And this is Dirac notation, which we're going to discuss a bit about it later in quantum mechanics. But basically, this type of dot products allows you to calculate shadows, the shadow that one vector projects onto another one. Later, we're going to use this to project onto subspaces, which is how much this vector projects on this span of other vectors. And that is extremely useful, as I will see today, because it allows you to talk about distances. It allows you to tell you how much this particular very complicated function looks like this set of less complicated functions. And last class, we actually had fun calculating the projection of these three-dimensional arrow in space by looking at the shape. Any questions of the summary of last class? Fantastic. Okay, to finish, the playgrounds that are kind of intertwined between, to be able to do playground 2, we needed to discuss more things. You see, this is a correct differential equation. Good job, Pablo. And I'm seeing that, oh, wow, I really screw up. I shouldn't have a square root in either of those things either. So I need to fix that. For those of you watching in many thousands of years, please forgive my typos in the differential equation. I will fix it. Anyways, these are the two playgrounds. On the first playground, you are expected to play with a numerical solver using Euler's method to see if you can actually get the solution of the differential equations that you know by memory what should do. I think I gave you one, the C version you don't have a solution, so you better solve it numerically, or otherwise you will not know how to solve that. And part 3 is intertwined with playground 3, which is to analyze the videos of the physics demonstrations that we have. Anybody has any questions with respect to the playground? Were you able to try them? Do you need any help? I think we're about to fix the forum so that we will have interaction within everybody. Apologies for the delay on that. But this is your moment to speak and say, Pablo, I need help converting the video to something that Python understands. Any questions with something else beyond the playgrounds? Has anybody else listened to the Hidden Brain podcast? This is the last time that I'm going to highlight it. Strongly recommended. Anybody has any comments? You listened to it?
Yeah, I listened to it. It's interesting. It's topics.
Very good. Very, very proud of you. Thank you for listening to it. So this is the last time that this will appear in here, but you know where to find it if you eventually want to come back and listen to it. It's very important to keep these things in mind such that you don't lose heart as you progress through your academic career. Okay, that is everything that I wanted to highlight from last class. Now let me stop sharing. And let's get into math. Oh, I need to make myself co-host. Still, I want to make you co-host. Are you SCH?
Yep, that's me.
Perfect. Okie dokie. Okay, so this is the menu for today. We have successfully finished the summary from last time. Let's talk about functions and vectors and projections as integrals. So let's think this together. Imagine that I have a function. My function f of x is equal to x squared times x minus 1. This function looks like this. I'm going to only analyze it between 0 and 1 to make my life easier. So this is f of x. If I want my computer to think about a function, it's really hard to give to the computer a function that is an infinitely continuous object, because then you have ever taken any formal math courses, these functions are defined on the real line. The real line is like gum, in the sense that whenever you're chewing gum, you can grab the gum and stretch it and stretch it and stretch it, and you can infinitely stretch your real line between 0 and 1. It has an infinite amount of numbers. It's way too much. So for the computer, one thing that you can do, you can say, well, if this is my x, I'm going to discretize my space, meaning this is x equals 0, another point in here, 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 dot, dot, dot. So if you discretize your space, you're basically saying, I'm not going to work on the real line. I'm going to create a list with the function values on that list. So I'm going to create f as a vector. I'm putting an arrow by just saying it's a vector in the sense, it doesn't have an orientation, but it's a list of numbers. And I actually like to imagine this thing as a very big arrow plotting in space. So what are the elements of this vector? Can anybody tell me? If I call this x0, x1, x2, x3, dot, dot, dot. And I have a delta x. Anybody has any ideas? What should be the values of this vector?
F of x0, f of x1.
Oh, fantastic. The first coordinate of this thing is f of x0. The second coordinate is f of x1. The second is f of x2, dot, dot, dot. And let's assume that I have n of these fellows, maybe n plus 1 because I started from 0. So this is the last one is x. Can anybody see that? I'm making a list of the values of this function on this grid. And if my delta x is small enough, this approximates my function relatively well. Why we would like to do that? Well, in particular, now integrals is something that you can define as just add all of these numbers together and multiplying by delta x. That will just be a numerical way of finding the integral or the area under the curve of this function. So I can say, for example, the integral of f of x dx is approximately the sum of f of xi, I from 0 to big N times delta x. I'm just adding all of these rectangles, which is what we already did whenever we were playing with Riemann sums. But this has many other advantages. The fact that I can think of functions as vectors, because now I can ask myself the question, well, oops. Imagine that on top of this, I also have another function. Let's put it in pink. Let's call this function sine of x. It's called g of x is equal to sine of pi x. Why pi? Such that when x is equal to 1, I'm basically evaluating sine function at pi. So it goes like this. And I want to ask myself the question, how much are f and g alike? I want to have a number. I want to have a notion of how much my function f looks like my function sine. Any idea on how I could do that? We touched upon that last week at the very end. So if you're thinking that you know the answer, most likely you do from the last discussion. Any suggestions?
You could discretize G over the same interval.
Mm-hmm.
And then for each value in that array, you could take the difference, which would be like a rough estimate of how different those values are.
I like that. That is true. You could basically say discretize G. So I'm going to make a G vector that is basically the same thing. G of x0, G of x1, dot, 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 G of xn. And what Virtual Josh is proposing is that then as vectors, you subtract these two things. That is a vector of numbers. And then maybe you take the norm out of that thing. And then if this is close to 0, then you're happy because these two things are very close to each other. Yes? Do you have any other idea of another number that could tell me whenever these two things are very close? Andrew. Andrew is talking in terms of projections, which is what we closed last time. So I also like that idea. Actually, that's the idea that I want to go. If you were able to calculate the shadow that f has on top of g, and that shadow is big, that means that these two things are kind of like each other. Yeah? How can we define projection operation between functions using what we know about vectors? And if you're thinking that you know the answer, most likely you know the answer and you can scream.
Like the dot product?
With the dot product, fantastic. So the dot product as vectors, see that now we have transcend the shackles of thinking of functions as functions. And now we're just thinking of our functions at these beautiful things. These, if I have discretized my space in 300 steps, my function f is a vector in a space of 300. And my function g is another vector in a space of 300, right? And we don't have absolutely any problem with that. We can work with those two. I'm just going to make the dot product between f and g. And this is going to be equivalent to putting the vector f horizontally. This is f of x0, f of x1, dot, dot, dot. I'm going to put my vector g vertically, x of s0, g of x1, dot, dot, dot. And this is basically f of x0 times, nope, times g of x0 plus f of x1 times g of x1 plus dot, 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 f of xn times g of x. Everybody agrees with this. And to some degree, we still need to play a bit with the norms of these things. We need to normalize them properly. But to some degree, this is telling me an idea of an angle between these two things. This is telling me if these two things are orthogonal, if two vectors are orthogonal, meaning that they don't cast a shadow on each other, their dot product is going to be 0. So if this number is very close to 0, this is telling me that these two things don't cast a shadow on each other that are very big. Yet if this number is very big, this is telling me they are very much like each other. Makes sense? Any questions so far? Please.
Why would you want to do one of these things over the other? The dot product versus.
You will see it when we play with the rope. That is a very good question. I am motivating this discussion in terms. By the way, some people, can you hear that question? Is the microphone working? You were not able. Is the microphone on?
Maybe I can talk directly into it. Can you hear me?
Okay.
Yeah,
So
we
can you
can
repeat
hear
your
it.
question?
What is the reason that you might want to take the dot product of two functions versus the subtraction that was first suggested?
And that is one of the reasons why I like to structure the class the way that I structure it. We're about to start playing with the rope. I want to give you motivations on why we are defining the objects we're defining such that they serve a purpose. Most classes usually are structured in a way where you're going over concepts kind of in, this is the first concept, the second one, the third one, but then I'm giving you answers to questions that you haven't made yourself. That's why we're going to play with the rope. Basically, what is happening in here is that the only motivation that I gave you to start this discussion is I want a notion of how much functions are close to each other. Why is it useful? That will be the question is, aha, I found a way of saying if function f is close to function g. So what? There is a very important application once you know the dot product, because you're going to be able to decompose your very complicated object into the shadow that it projects into less complicated objects. We're going to study those less complicated objects separately, and we're going to be able to make progress on real life applications. Just subtracting them will tell you if they are close to each other, but then you cannot do anything with that information beyond just being happy that they are very close or very separate from each other. Make sense?
Yep.
Perfect. So the next thing that before we go and we play with the rope, I want to draw your attention that what I just wrote in here is the sum of f of xi times g of xi, I going from 1 to n. No, from 0. Do we know any other way of writing this? And I'm seeing virtual Josh nodding.
You could use Einstein notation.
I could use Einstein notation, that is true, but I'm thinking of something else. Does this remind you of something? Let me zoom back a bit. Okay, this might be hard. Almost there. Can you see it?
The integral?
That is an integral, right? Let me grab it here. If I bring this down, I put it in here. Now that we have discretize our space, this sum was equal to this integral. So if just by chance I decide to, let's just multiply this by delta x, how much this is equal to? Or approximate to?
The integral of their products.
Fantastic. F of x dx, and I'm going to define this as a dot product of f and g. Or using direct notation, this is f. That is a definition, but it's a definition that I'm making because it's useful. Because thinking in terms of vectors, integrals seem to be the perfect generalization of what a dot product means in terms of vectors, but now translated to functions. And dot products in a space of vectors allows me to talk about shadows, which is going to be extremely important for what we're about to do with functions. But we need to make that connection. If I just told you the dot product between functions is defined as an integral, okay, why? This is why. Make sense? Okay, let's go and play with the rope. Now, let me think how we're going to do this. Okay, let me just briefly draw what is about to happen, just in case the quality of the video for some people is not the best. I'm going to require a volunteer from the audience. I'm going to stand in here, and that volunteer is going to stand on the opposite side. And we're going to have a rope that we're going to handle between the two of us. And then we're going to start vibrating the rope. And the questions that I'm going to start asking out of everybody is, for a given initial condition of the rope, is it possible to predict with equations or with mind power how the rope is going to evolve in time? That is what we're trying to address in here. So let me stop sharing here. Let me pin this. Okay. Okay. Who wants to help me from the audience? Fantastic. Okay. Okay. Will you be my cameraman? You can go around and capture the entire scene. Okay. Sorry? Video. Okay. Zoom folks, can you see me?
Yeah.
Fantastic. So the quality of the video might not be great, but that's why we're going to have an edited version for YouTube. So go. Okay. Come a little bit closer. Okay. So everybody's seeing the rope. I will interpret that as a yes. So we can move the rope. We can move the rope around, and it's going to do weird stuff. Everybody can see it? Can see that. So my question to you is that if I were to say, well, all of you are physicists, that's what I have heard. That means that you know how to describe mechanical systems. You did a spectacular job on the playgrounds whenever you were trying to describe the pendulum and the spring. So if I were to offer you a year supply of free ice cream in the data store in here, if I were to put this in some initial position, do you have the tools in your hand to be able to predict how this rope is going to evolve as a function of time? Anybody has an idea? How will you tackle this? It's an entire year supply of free ice cream. Any
Well,
idea
you can
from
start with
folks?
how the hands are moving.
I cannot read anything that you're typing. I'm sorry. If somebody reads it for me, I will be able to hear it. And can you repeat what you said?
The chat says force diagram first. I said we could start with how the hands are moving, and then.
So you mean, let me increase the volume. You mean making a force diagram?
That's what chat says, yeah.
You could do that. The problem is that the rope is a continuous thing. So force on where? So one thing that you could do is you discretize the rope into little marbles, and you try to understand the forces that are acting on each marble. And that will eventually take you to the differential equation for the rope that I'm going to write at some point. So that is a good way to start. But then how do you solve that? Any other ideas?
Don't you need to know like
Probably, yeah. But if I give you a picture of the rope in a specific initial condition and I let it go, so I tell you the rope is starting at 0 speed, would you be able to figure out the evolution? Let me help you a bit. What if instead of any initial condition, try to hold it very tight? The initial condition that I give you is something like this. This is just hold it steady. There you go. What if this is the initial condition? I just take a picture of this and I ask you how it's going to evolve in time. Can you predict how this is going to evolve in the next seconds? Andrew says yes. What is going to do? Can you show me by show of hands? It's just going to move up and down, right? So if I have this mode that is a special mode, somebody's trying to say something or you're just unmuted by accident? If you're unmuted by accident, Till, can I know you to mute folks? Thank you. So if it's
Yeah, I
in
think
this position, you see that the evolution is going to be trivial, right? What if it's in this position instead? Hold it tight. What if I give you this starting initial condition? Ah, this is a different one. Are you able to predict what it's going to do as a function of time? Now I want somebody from Zoom. Can you tell me? Can you see it well enough? Raise it a little bit so the contrast. Can you see what the rope is doing?
yes,
Will you be able to predict this as a function of time?
yes.
What is the difference between these two things? And you're very smart, all of you, so you can extrapolate what I'm going to do next if I can. This is really hard. But the next mode, I almost got it. Aha, there we go. You also will be able to predict it in this one. What is special about these things? Any ideas?
One side is allowed to move at specific frequencies and one side is held fixed.
Yes and no. You saw my hand moving. Thank you, Josh. You saw my hand moving because I had to move the rope. But in principle, this is something that you could model as both ends of the rope being stationary. Have you seen this behavior before? I'm preparing everything, so it may take me a few seconds to get back to you. But has anybody seen such behavior before in any other systems?
Yeah. As a cello player, yeah.
Yeah.
Aha, in where?
The strings on the cello.
As a cello player, that makes sense. Yes, actually, that is exactly the same thing that is happening here. These are called by many names. I'm going to call them resonances or normal modes. Let me go back to my screen. Thank you so much. You were a fantastic assistant. Aha. So this is hard. But if I were to put it in something like this is easy. Because this is one of the normal modes of the rope. It's a mode in where the time evolution of this thing is just trivial. The thing moves up and down, and that's it. There is nothing to think. The same as all the other normal modes that I'm having. Make sense? So here's the crucial part. And that is the part that I want you to think. After this, we're going to go into the actual activity, class activity, and then we're going to take a break, and then we're going to come back to matrices and linear algebra. Here's my question for you. So this was easy. If you were to put the rope in this other mode, this was also easy. Let me call this, let's put colors, different colors. Let's call this G1 of X. Actually, it's X and time. Let's call this one G2 of X and time. And the next one, let's put it in orange. This is the next normal mode. I am at my limit on how to draw these things. This is G3 of X and time. Here's the insight. If somehow, let's call this one is F of X and time. If somehow I was able to write f of x and time as an approximation of a coefficient a1 times g1 of x and time plus a coefficient a2 times g2 of x and time plus a coefficient a3 times g3 dot dot dot. If I were able to do that, if I can find these approximations, then my life is going to be very easy because I know how each term on the right-hand side evolves as a function of time. So if I want to understand how the left evolves as a function of time, I just evolve each one of these terms themselves, and I'm going to understand how the whole, at least within this approximation, is moving. Is that goal clear? Everybody understood that? Or is there anybody that wants more clarification on where we're heading? Now, this is the reason why people in quantum mechanics are always obsessed with diagonalizing the Hamiltonian matrix and finding the eigenstates of your system, the eigenvectors and the eigenvalues. These are those eigenvectors and eigenvalues. Those are the states under which your operator looks trivial. The operator that I'm talking about today is a time evolution operator. That's what I'm saying when I say you hit play and the rope starts moving. And what I'm interested are the states in where when I hit play, the time evolution that they have is just so boring. It's just moving up and down. And if I'm able to understand what are those states for this specific system, it's going to be much easier for me to understand what a general state in where I prepare my system is going to evolve like. Make sense? That is a goal. Funny enough, this is how a big part of the technology of telecommunication worked, at least until some decades ago, in where whenever you're talking on the phone with somebody, your voice is transformed into a signal in where we then do a Fourier transform. It's literally this, basically. And we obtain those coefficients, and those coefficients are what is sent across space to the receiver in the other end that grabs those coefficients, decomposes, creates the signal based on those numbers, and that is what displays your voice on the other side of the transmission. Okay, let's do the activity because I have been monologuing for 40 minutes and Frank and Josh will be looking bad at me for monologuing for so long. No? Okay, thank you. So here's the activity that I want for you to do with you. These coefficients, there is some details that we need to argue on for this to work, but for now, I just want you to try them. You can obtain these coefficients. A1 is going to be equal to the dot product between F and G. AI. These are the shadows. Basically, these coefficients are telling you how much your original function projects on this new basis that is going to be the basis of eigenstates. Now, for this to work, one thing that needs to happen is that the GIs have to be orthogonal, have to be orthonormal, actually. That means that if I were to do the dot product between G1 and G2, I get 0. But if I were to do the dot product between G1 and G1, I get the number 1. This is basically telling you that you have a basis, a vector basis, that is normalizing where this is your first unit vector, G1, and this is your second unit vector, G2. They are orthogonal, their size is 1, so whenever you calculate projections, you're literally calculating the shadow, etc., etc., etc. So your task is, and I'm realizing that we're going to need Wednesday to talk about linear algebra as well, but your task is to do this for the rope between 0 and 1, and my initial function is the function that we were discussing before, is x squared times x minus 1, and your normal modes, GI, these are going to be some amplitude times sine of I. Okay, this I is a bad idea because you're going to think that is the imaginary number. So let's put it as an n. Gn are sine of n pi x. In order for these things to be normalized, you need to divide by 1/2. So your task for the next 5 minutes, and then we're going to compare those numbers with an animation that I have made, is to calculate the first A1, I don't know, let's say up to A5, maybe, between these two things. So for example, a1 is going to be the integral of f of x between 0 and 1 times 1/2 sine of pi x dx. And you can use any numerical integrator that you want. For example, you can do this by hand. These functions are integrable by hand. But if I were you, I will go to Wolfram Alpha, and I will plug in these things and say, please tell me what is the value of the integrals of these functions. We have 5 minutes for this, and then we're going to discuss on 5 more minutes, and then we're going to stop for a break, and then I'm going to continue monologue. So it's 2:12. Give that a try until 2:17. And by the way, okay, I forgot about that. We have some Zoom participants. What I'm going to do in here, I'm not going to stop recording because it's easier to just have a single file, but I'm not going to add this into the recording that is going to go to YouTube. I'm going to mute myself here, and I'm going to lower the sound. Till, are you here with me?
Yep.
So
Yep.
Till is going to guide the discussion on Zoom so that you can also participate. I know it's hard, and if you don't feel comfortable talking about this as we go through the activity, that is completely okay. But let's give it a try and see if we can have interaction between Zoom folks as you go through how you will integrate these things and find these numbers. And then I will be back unmuted at 2:17. Okie dokie, I'm unmuting myself. Zoom folks, can you hear me?
Yep.
Perfect. Okay, so I'm going to show, I hope that everybody got some of your numbers. I'm going to start asking for numbers in a second, but an important question that came from the in-person folks is why specifically we're using these functions. I claim that these are the normal modes of the rope. Anybody has any more arguments on why these are the functions that we want to project upon? The person that asking here asks, well, can I use any functions that I want for these g's? And of course you can. It's just that it's not going to work in terms of describing the evolution of the rope. Anybody knows why?
Because they're nice and predictable.
They're nice and predictable. I agree, but they have to have another problem. It cannot just be that.
It doesn't
I
give
didn't
us
give you any
a
detail.
time.
Go ahead, sorry.
It doesn't tell us how they change with time.
Well, yeah, we're missing a time component, but that is not the important part. It's just that I didn't give you any of the details. I should have. The differential equation that we're trying to solve, whenever you sit down and you discretize your rope, and you write down the differential equation that this system is going to obey, the differential equation looks like f of x t is a partial differential equation in x and time. It looks like this, minus d dt square. It's a minus or a plus? I think it's a minus. 1 over v square f of x and t is equal to 0. You're looking for a function of x and time, which if you make 2 derivatives with respect to x, is the exact same thing as multiplying by a number times 2 derivatives with respect to the time. This number is the speed of wave propagation in the rope. We will discuss this more in detail later whenever we have classical mechanics discussions. But now you are faced with a partial differential equation in 2 variables of second order. Very scary. And you're like, I have no idea what is going to be the solution to this differential equation. But if you think of this as an operator and you're trying to see what are the normal modes of these things, what are the functions that kind of satisfy this differential equation almost by definition, the functions that you are not obtaining look like this. Sine of some constant times sine of n pi x times cosine of n pi t. There is a v somewhere here. I don't remember. I need a v. There is an L as well. I think there is an L, and maybe there is a v here. V converts. Yes. It's not necessarily exactly this, but it is related to these functions, and these are the functions that then you expand upon, because these are kind of the eigenstates of this differential equation operator that you have. So this thing, whenever I told you to expand in this specific function is a very important function that is tied to this differential operator. These are the functions that solves the differential operator in here. And whenever in the future you see, for example, when you're going to do electricity and magnetism and you're going to solve the Poisson equation or the Laplace equation in Cartesian coordinates or cylindrical coordinates or spherical coordinates, so you're going to be using the Bessel functions or the Legendre polynomials and blah, blah, blah. Those are the eigenstates of those operators in those coordinates. And that's why you expand on this. Make sense so far? At least the idea of what I'm saying, the details don't matter. We will go through those later. So that's why these are the important functions. Okay, let me stop sharing with my tablet and let's look at the animation. Oh boy, today I really miscalculated my time, but it's okay. Okay, so I created these. Let me actually go to. I created these notebooks for animations. So if all of you go to the online guides, and remember how we do code spaces, you go to the GitHub repository, you click in code, you create and adding one extra code space, and that is going to take you to this space that is the virtual machine that you can use to run the code. And I have put in the math part rope equation animations. So that's what we're going to study now. And once you install Python and enable the Jupyter Notebook extension and yada, yada, yada. Open anyways. Yes, just open this. You will see the following code. So this code was made between me and ChatGPT, iterating over the weekend. I think it came out very nicely at the end. Okay. But of course, if you know what you're doing in terms of coding, feel free to modify this. So if you run the first part, what it's going to do is going to tell you these coefficients. We're going to look at yours in a second. But then in here, you can, we're going to plot in the coefficients that you have. So user coefficients, okay. So can somebody tell me the first two coefficients that you got? I need volunteers. I need numerical numbers. Anybody got those projections for?
Yeah, for the first one I got minus 0.0323. I don't know how far out you want it.
I think that's okay. And the next one?
0.0121.
1, 2, 1. Okay, so let's see if this works. Is this where we're using your coefficients? Use coefficient. Okay, perfect. So this is an animation of the rope. Yeah, I think you got the correct coefficients. So in blue, you're seeing the actual rope solving the partial differential equation numerically that I mentioned before. And in red, you're seeing the evolution that you obtain if you project into two normal modes. Very good. Congratulations. You want to tell me the third and the fourth?
Sure. Ready?
Yep.
Okay. Third is minus 0.0012.
Uh-huh.
And the fourth is 0.0015.
0.0015, right?
Mm-hmm.
Okay. Now let's. Something I screw up in some way. What did I do? Oh no, it's still running. Okay. No, wait. What? Okay, my bad. I was running something different. Do you use the 1/2 for your projections?
Yes. I am not sure why I screwed up.
You have a factor of 1/4 that is inconsistent. Okay, let's multiply this by 4. Maybe we made something weird with the math. Let me run it. You working, computer? Okay, there is something weird with a factor of 4. I will analyze that later. but this is what we get with your coefficients. You see that now the difference is even smaller between the true rope and the approximated solution. And now let me pause it instead of continue taking your coefficients. Thank you so much. That was fantastic. Maybe my Python is just automatically taking into account that one half. But user coefficients, blah, 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 let's use 10. So if you were to do the projections and use 10 coefficients, this is what we get. My computer is slow. I think I clicked it twice and now it's angry at me. This is what happens if you use 10 bases of your normal modes. Basically, you really, really cannot distinguish between the two things. And the more you include, you're going to approach these closer and closer until eventually you cannot see the difference for real. Make sense? This is what is happening to your voice whenever you decompose it in Fourier. This is what is happening to your eigenstates in your Hamiltonian whenever you find the basis of eigenstates for your system. And this is how it works. The final animation that I wanted to show you is all the normal modes, how they look if you were to plot them together. You're decomposing your problem into a linear superposition of these 4 or 5 things. And you see that each one of them has different numbers of nodes, and each one of them oscillates at a different frequency. And the combination in a specific way with specific coefficients of each one of these things, it is what gives you back the evolution that we were showing. And now I have okay, there we go. Any questions so far? Excellent. Okay, so I have lost Zoom. Did I disconnect from Zoom?
You're still here for me.
Ah, okay. How do I come back to Zoom? I cannot go back to Zoom. Okay, there we go. Stop sharing. Thank you. Perfect. Thank you, Josh. Okay, so let's take a 5-minute break. It is 2:27. We'll be back at 2:32. Go to the restroom, and I'm going to think on exactly how to talk about the other things that I want to do. See you in 5 minutes, friends. Very good. I'm coming back. Zoom folks, can you hear me well?
Yes.
Perfect. Let me share screen again. Okay. So I have 25 minutes. Let's try to go over the next things that I want to say with respect to linear algebra. And whatever I don't get to say, I will say on Wednesday, when we also talk about the miscellaneous topics. So the key insight, how do I write insight? Insight. I hope that is a way to write it. The key insight is for operator I'm going to make this as general as possible. Here's the palm tree again. You have an operator that I call palm tree because it can be anything. It can be a matrix, it can be a differential equation, it can be, well, either of those two. For this operator, if it is linear, and turns out that many linear differential equations are linear, and linear algebra, as we're going to see in a second, matrices are linear. If it's linear, is a good idea to find its eigenstates, eigenvectors, normal modes, boring states. I'm coining this name, but basically states on which the operator acts, and it gives you something that is very easy to understand. That is what happened with the rope. The operator was the differential equation of the rope and the evolution as a function of time. We found these normal modes on which the operation looks trivial. Why is that important? Because then you can decompose a complex solution as a linear superposition of these easier to understand states. Make sense? Fantastic. Let's now think in terms of linear algebra. Coming back to that, we started talking about vectors. Now I'm going to come back to vectors of, linear algebra, matrices of size 2 by 2, 3 by 3, if I'm talking in 2 dimensions, in 3 dimensions, etc. And it's going to connect with what we have discussed so far. The example of the matrix that I want to use in here is this one. It's one of my favorite matrices because it's very nice to illustrate what it's doing. It's a 2 by 2 matrix. A 2 by 2 matrix acts on vectors that live in 2 dimensions. So if I have a vector, let's say the vector 2, 1, let's say 3, 1, so that we have different numbers. This is V. Then my matrix M, if you are unsure on how to multiply vectors and matrices, I mega encourage you to take a look at the linear algebra resource that Thiel put together. This operation is equal to 2, 1, 1, 2, acting on the vector 3, 1. Can anybody tell me how much this is?
7, 5, right?
Perfect. Yep. So that is going to be a new vector that the first coordinate is 7 and the second coordinate is 5. It's going to be something like this. This is M acting on V. M acting on V. It's a new vector. So basically, the action of this matrix is to turn this friend, it makes it this friend. It's going to do something to the vector. And this linear matrix, this linear transformation is going to do things to all the vectors that can live in here. The analogy that I want you to carry over, why are we interested in these things? Why start writing matrices on the first place? I like to think of this as cooking. I like to think that my vectors are ingredients and my matrices are operations that you can do on those ingredients. For example, my ingredient could be an onion. An operation that I could do on any ingredient is cutting, chopping it. So if I apply the operation chop to the state onion, what do I get?
Chopped onions.
Chop onion, of course. If I apply the operator chop to the state chocolate, what do I get? Chop chocolate. If I apply the operator freezing to a glass of water, what do I get? Ice. Maybe broken glass if the glass was made out the glass was made out of glass, but yes, I get ice. What happens if I apply the operation freezing to ice? What do I get? Let's write that down. I'm going to write that down. So if we think it that way, the operator C for chopping, I can act on the state onion, and this is equal to chopped onion. If I act with the operation freeze on the state water, I get ice, right? What happens if I apply the operation freeze to ice? What do I get?
Ice again.
I get ice again, right? You grab a piece of ice, you put it back on the freezer, you wait for a day, you just get ice. What happens if you apply the operator chopped to, let's say, we don't have to be that creative, chop onion? What do you get?
Chopped onion.
You get chopped onion. So the two things that I want to highlight with this silly example about cooking, the first one is, I want you to think that the reason why we're doing all of this nonsense in terms of linear algebra is because as physicists, as scientists, as engineers, we're going to be very interested in doing things with our vectors. For example, maybe we're describing the movement of a particle as it's traveling to space and it's doing X, Y, or Z. Or I'm trying to understand the electromagnetic field that is produced by some charges that are distributed in this way. Or any of these applications, we're going to start doing operations to a set of vectors, and those operations are going to transform those vectors in different ways. And we're interested in going from an initial state of vectors to a final state in where after applying all of our operations, we get something that is of meaningful value to us. That is the exact same thing that is happening whenever we cook. You have ingredients and you want to make a cake for somebody. You start with your ingredients, you start applying operations one after the other. By the way, operations not necessarily commute. It's not the same to chop water and then freeze it than to freeze water and then chop it. You're going to obtain very different things. In one, you just get ice because chopping water, just applying chop to water gives you water, so nothing happens. And then freezing it will just give you a solid block of ice. But if you were to freeze it first and chop it later, you get crushed ice, which is a different object. So another important thing in these things, these operations not necessarily commute. The order matters. But anyways, you're trying to apply these operations in a specific sequence to start from your ingredients to the final objective that it might be a cake that you want to make from someone. That makes sense? So that is the reason why we're trying to study these operations. Among the many operations that you could do to vectors, a very big pool of operations is called linear operations, and any linear operation that you can think of that you can apply to vectors, you can write it as a matrix. That's why we talk about matrices, and that's why I'm going to spend 10 minutes talking about this specific matrix. So let's go back. So that was the first insights that I wanted to give. The second insights that I wanted to give is that for any operator, there seems to be some states that are the boring states that we're after. These are the eigenstates, states in which if you just apply the operation to the same state, you just get to that state, you just get basically the same state. When we said that cutting, did I call it cutting? Is that the operator? Okay, chopping. When I said about the operator chopping applied to chop onion, now that I'm thinking about this, I disagree. I don't get chop onion. I get further chop onion because I'm going to chop it further. But it's kind of the same. It's basically multiplying by a number, which just make it more chop. It's not going to transform chop onion into celery, which is going to be a very complicated transformation. So let's now analyze the transformation that I started with, which is my matrix M. So suppose that I were to ask you, I'm interested in understanding what this matrix M does to the entire plane. We just saw that this vector V gets mapped to this other vector. Question. The vector 1, 0. Let me bring my matrix. Where does 1, 0 gets mapped through this matrix? Any suggestions? Some folks.
It maps to 2, 0, I think.
2, 0? 2, 1. Yes. That one I like. So if you multiply this by the vector 1, 0, you get 2 and 1. Okay, so that rotates this vector a tiny bit, like around here. This gets mapped in this way. What about the vector 0, 1? Let's call this is V1, this is V2. Where does V1, V2 goes to? So M applied to V2, you say that it goes to the vector 1, 2, right? So that, let me put it a different color. This is going to be a bit messy, but that kind of gets mapped here. Question. If I were to give you a vector in black, let's say this friend, without doing any calculation, can you see in your mind's eye where this vector is going to be mapped?
It'll trend towards the 45-degree line, y is equal to x.
Right? We are seeing a pattern. There seems to be, let me put it in here, dot, 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 dot. There seems to be a line in the 45-degree angle, which most vectors seem to try to converge to that line, and they get stretched along that line, right? What do you think will happen if I look at, for example, a vector that is orthogonal to that line? What will happen to the vector v equals -1, 1? What happens to this vector without doing any calculation? What does your intuition tell you? Is it going to try to go through that line? Andrew says it doesn't change. Let's apply it. M applies to V. 2, 1, 1, 2, -1, 1. This is equal to 2, 1, -2. So this is -1. And this is 1. So the vector stays the same. This is one of those special vectors. The other special vector in this case, and I'm trying to think how much time I have to devote to this, is going to be this vector 1, 1. And if we multiply the matrix by that vector, M times 2, 1, 1, 2 times 1, 1, I get a vector that is 3, 3, which is 3 times the vector 1, 1, which is a vector that we started with. So there's two special vectors in this plane on which the operation of this matrix looks trivial. Those two are the eigenvectors of this matrix. And if you write it in terms of these vectors, the problem is that I have too many arrows. If I rewrite my thing and I say, well, this is my first special vector, let me call this phi 1, and this is my special vector phi 2. The action of this matrix is going to grab this vector and it's going to multiply it by 3, and it's going to grab this vector and it's going to multiply it by 1, and it's not going to do anything else. So this matrix is basically stretching everything along this line, multiplying it by 3, and this line is leaving it alone. So if you were to make a picture, and that this is going to be your homework or your playground for the next class, and then I'm going to address this in a bit more detail, basically it's going to look something like this. This is the operation that this matrix is doing to the whole space. Is stretching things along that diagonal direction and is leaving the orthogonal direction alone. How do you find these things? Part of your homework is going to go through the resource that Till put together on the eigenvalues and eigenvectors of matrices. I am going to talk about that for the next 5 minutes, and then we can wrap up the session. But as an intuitive idea, the thing that you will do is say, I'm interested in saying my matrix M times a vector V. I want this to be equal. I'm trying to find a vector V such that the action of the matrix applied to that vector gives me a number times the same vector. This number, most people call it lambda. And I am most people, so I also call it lambda. This is an eigenvector equation. By the way, is it clear why we will be obsessed with finding these two vectors, phi 1 and phi 2? It's because then you can see what the matrix is doing to the entire plane without having to calculate the operation of the matrix on each one of these vectors. You can have an intuition on how the transformation looks everywhere. Does that make sense? Anybody has any questions with respect to that objective? Okay, so How do we deal with this? We're trying to find the vector and the eigenvalue that satisfy this equation. Anybody knows how to proceed? Have you ever seen this before?
Yes, you
Okay.
subtract the right-hand side from both hand sides of the equation.
Very good.
You take
Let's
the
say
norm.
this is equal to 0, and then what?
You take the norm.
I take the norm, and what do I do with it?
Sorry. So the manner in which that is equal to 0, excluding the case where the vector is not the null vector, is when m minus lambda times I is equal to 0.
Yes and no. Let's go by parts. You're close, but let's be a bit more formal. This operation equal to 0 makes sense to everybody here. Let me factorize this. This means m minus lambda. All of these apply to the vector v is equal to 0, and I have to be careful because m is a matrix, lambda is a number, so this will not work. I have to put an identity matrix here. This case is just 1, 0, 0, 1. It's just a matrix that is diagonal, is the equivalent of the number 1 in matrices. So this is what I'm after, right? But now what you're seeing is that I am after a vector v such that the action of this entire thing on that vector is equal to 0. Because of math properties, a matrix that has that ability to grab vectors that are non-zero and eat it all completely and map it to 0, basically chopping the entire vector, is killing the vector, that is a matrix that we call them singular or non-invertible. So m minus I lambda must be a singular matrix. And one property that singular matrices have is that their determinant is equal to 0. You can think the determinant, again, I encourage you to look at the resource that Till put together, but you can think of the determinant as something that tells you the size of the volume of the hyperdimensional space whenever the matrix acts on it is going to stretch things in a specific way. And if it stretches it a lot, the determinant is going to be very big. But if there are some vectors that the matrix is collapsing to 0, it's going to basically kill the entire hypervolume of the transformation. So what you do, you say, let me calculate the determinant of m minus lambda I equal to 0. And now you can, bye friends. Now this is an equation that you can play with. So you're trying to find the determinant of this 2 by 2 matrix. I'm almost on, and then I'm going to stop. Let me just write it in here as an example. This is your 2 by 2 matrix that we were describing, minus lambda 0, 0, lambda. I'm trying to calculate the determinant of this. This is equal to the determinant of the matrix 2 minus lambda, 1, 1, 2 minus lambda. And calculating determinants is extremely annoying for anything that is not a 2 by 2 matrix. So very lucky that I pick a 2 by 2 case. Is a multiplication of these two minus a multiplication of these two. So this is going to be 2 minus lambda times 2 minus lambda minus 1 is equal to 0. This is what the determinant of this matrix is equal to. So if you expand this, you're going to get 4 minus 4 lambda plus lambda square. Did I do this right? Minus 1 is equal to 0. Something tells me I didn't do this right. Is it right? Yeah, I think this is right. Which is equal to lambda square minus 4 lambda plus 3 is equal to 0. And I'm trying to find the two roots of this equation. Everybody follow, or I have lost people? Yes? Some folks?
Sorry, what was that?
Are you following what I'm doing? We're trying to find the determinant. This is our master equation. We're trying to find the value of lambda that will make this happen. So we went through all the process of calculating the determinant, and we arrive at this equation.
Yes.
So I'm trying to find two values of lambda that fulfill this equation. And if I haven't done my things incorrectly, I'm going to claim that lambda equals 3 and lambda equals 1 are two values that are going to fulfill this equation. Let's see. If I plug this in here, this is 9 minus 12 plus 3, and indeed this is equal to 0. If I plug this in here, this is 1 minus 4 plus 3. This is indeed equal to 0. So yes, I found the two eigenvalues. These are the two eigenvalues, by the way, that we already knew when we were playing with. This is the 3 that I have in here, and this is the 1 that I have in here. So now you have found the eigenvalues. You need to find the eigenvectors, and this is the last thing that I'm going to write, and then we're going to stop, and you're going to try this for the next class. The way to find that, you're going to write your equation, mv equals lambda v, and you're going to substitute the numbers that you got. Now we're going to plug in here 3. So m is 2, 1, 1, 2, acting on the vector x, y, because I am unsure of what this vector is. This should be equal to 3 times the vector x, y. And now I'm solving for x and y to find what are the values of this eigenvector. And you're going to find out that x is equal to 1 and y is equal to 1. And this is, or 1 over square root of 2 if you're trying to make this thing normalize. So this is what I wanted to say, a bit rushed in terms of eigenvectors and eigenvalues, and in the case of this matrix. Next class, what I want to go over is how do you do a change of basis to express any vector as a linear combination of these phi 1 and phi 2. Basically, is the exact same thing that we were discussing in here whenever I was trying to write this equation. Whenever I wanted to say, how can I write my generic function f as a linear superposition of the normal modes or eigenstates of my system? That is what we're going to try next class. And next class, we're also going to go over some of the miscellaneous math topics. No matter what, we finish with math this Wednesday. And if there are things that I consider that are important to also discuss, I'm going to just record them and I'm going to upload them to YouTube, and you can see them in any time that you need. So before I close, let me share again, just to go over the playground with you, because I thought that I was going to be able to cover more, but it is okay. So your playground for this week, check the linear algebra notebook that Teal put together. I would love if you can grab this matrix that we discussed in class. In this case, go over the calculations that we did so you feel a bit more comfortable. But in particular, if you were able to do this in Python, some sort of vector plot as the one that I was showing, that you can show how each vector gets mapped to what, so that this picture of the coherent action of this operator on the entire plane appears. And I suggest, if you want, try the same thing with a 3x3 matrix that you create by yourself. Josh has been a master of creating 3-dimensional matrices and looking at the eigenvectors recently because of research. And here is the final thing for the next class, that we're going to be covering these miscellaneous topics. The next class is in 2 days, so try to input anything beyond complex numbers, Fourier transforms, and distributions that you would like to see. Any questions before we all go in our separate ways?
I have a question about the complex stuff we're going to cover on Wednesday. Does that including things like the residue theorem and de Moivre's theorem?
The residue theorem, most likely yes, because you're going to want to use that to calculate. No, wait, I am. What is the residue theorem? I was thinking of something. Yeah. Cauchy's theorem, basically, that integrating complex functions gives you multiples of 2 pi i's. Yes, we're going to cover that very lightly. We're going to have resources for those, but yes, we're going to talk about that. Somebody is asking me about the dates of the subject exam. I have no idea. That sounds like a Remco question. So my recommendation is email Remco. But for classical mechanics, I think is mid-August. I think you arrive here, you have your orientation, and then you take the exam, or maybe you take the exam before the orientation. I don't remember. Where to find the link to the Google Drive for the playgrounds? Yes, so if you go, let me share my screen again. Take a picture of this. This is a folder link. And in the folder link, there should be, let me put it in here in case you need to take a picture. In the folder link, you see the playgrounds folder that is in there. If you cannot find it, send me an email. My email is here, and I will put you in contact with that. Perfect. What else? I was discussing something else. Any other questions? Okay. So I wish that you all have very good rest of your afternoons and rest of the week. I will see you on Wednesday. And I hope that from now on, any time that you're thinking about linear operators and matrices and differential equations, you imagine chopping onions and playing with the rope and finding the normal modes. Godspeed, friends, and I'll see you next time. Thank you, some people.